All right, folks, good morning, good afternoon, good evening. Whenever you are watching this, I hope all is well. It's me, Dr. Kaz, and I am going to talk about a fun chapter, or chapters, I should say, chapters 2, 3, and 27. So some of this is going to be review, but this is one of my favorite chapters, and I know I say this quite a bit, probably about almost every chapter that I go over, but this one's really fun and exciting because we're going to be talking about metabolism. We're going to be reviewing some things. We're going to actually kind of draw several concepts together as we go through this chat session today. So let's start off by defining what metabolism is. And this is important. And I do recall in my previous classes, way back when I first started teaching anatomy and physiology, this is one of the early concepts that I talk about is what metabolism is. And basically, metabolism are just chemical reactions, but since we're dealing with living organisms, they are biochemical reactions that occur in all living things. And so if you haven't taken a chemistry course, it's okay. We will keep it very simple, but we have to start off by talking about what exactly these chemical reactions are. And essentially what we're going to see is, and we learned way back in chapter 2 when we were learning about molecules and atoms and all that fun stuff, that chemical reactions are going to be basically, we know that we learned about the different types of bonds that occur between molecules. And what we're going to do is we're just going to break these bonds. We talked about how these bonds form. We have different types. You have covalent, you have ionic. And so now we're going to talk about breaking these bonds. And then in some cases, what we'll talk about then is how we form new bonds. And so to kind of put everything down on paper, as one would be able to easily to understand this, we write it out, much like a mathematician would write out an equation for mathematics. Well, chemist writes out an equation, regarding chemicals. So we're going to use chemical equations, and we're going to talk about what reactants and products are. So when we're dealing with reactants, these are the stuff or the things that we start off with. And so we'll have these at the beginning of our chemical reaction. And so when we're writing out our chemical equation, we'll see, all right, the reactants on the left side. And so what will happen is we undergo a chemical reaction, and then what we're left with are what we call the products. And these are going to be the things that form during the reaction. And we're going to see those things on the right side of our equation. So when we're looking at this formula here, A plus B, and then the arrow is indicating C, all right, everything on the left side of that arrow, those are the reactants. So A and B are the reactants. And then everything on the right side of that arrow, those are going to be the products. And so as mentioned here, that arrow is going to tell us in which direction this reaction is moving. So it's just basically saying that our reaction is going from the left to the right. So A and B, right? We're going to have an interaction with A and B, and we're going to form C here. And so we're going to go through and talk about some of these different types of chemical reactions. So there's three criteria that we classify these chemical reactions with. All right. One is going to be changes in the chemical structure. All right. The second is going to be changes in chemical energy, very important, especially when we're dealing with ATP. And then finally, whether a reaction is irreversible or reversible. So the three types of reactions that we're going to talk about, all right, that change the chemical structure are decomposition reactions, synthesis reactions, and exchange reactions. So the first one here, or decomposition reaction, is catabolism. And we've talked about what catabolism is. Catabolism is when we start with something and we kind of tear it down. You're going to start with something big, and then you're going to make it into something smaller. So digestion is an example of catabolism. You're going to be putting some fruits, vegetables into your mouth, and we're going to break those fruits and vegetables down into their proteins, into their amino acids, into carbohydrates, simple sugars, that sort of thing. So we'll start off, all right, initially with something that's going to be large, and then we break it down into something that's smaller. So our chemical reaction that you see here, AB, right, undergoes a chemical reaction, and then we're left with A plus B as our products here. So an example is the hydrolysis reaction. Now notice the term hydrolysis. right, has to do with water. And so when we're dealing with hydrolysis reaction, we're starting with one of our sugars here, sucrose, right, table sugar. Okay, when it undergoes a hydrolysis reaction, we break it down into what we call our monosaccharides, our simple sugars, which are going to be, in this case, glucose and fructose. So if you look down at the equation at the bottom here, you'll notice here we are with our molecule, our sucrose molecule. Okay, it's a disaccharide. And so what happens is it undergoes this hydrolysis reaction, okay, which is a decomposition reaction, which we break it down into two smaller items. During that process, water is added in, and we are going to take water, the molecules of hydrogen and oxygen, and we're going to add it to, all right, our two products here, and we're going to yield a glucose molecule and fructose. And if you recall, glucose and fructose will, all right, when we join those together, will form sucrose. Glucose is going to be involved in all our disaccharide molecules. We'll talk about that later on. All right, the next type of reaction is a synthesis reaction. This is where we're going to make something. We're going to start off with something that's small, two, three, whatever. We have a bunch of small items, and then we're going to combine them to form a larger structure. So we're basically kind of doing the opposite of what we just did in the previous slide there. So we call that anabolism. So anabolism, you think, this is what I tell folks, after you digest stuff, and your digestive system now has all these amino acids and whatnot, and they're going to take those amino acids and they're going to try to build, okay, dipeptides, polypeptides, and proteins here. So what we're going to see now in this situation with anabolism, right, a good example is the dehydration synthesis. And when you see that term dehydration, you should be thinking of, okay, we're going to extract water out of this reaction. And so here's what we're going to see. We have two individual amino acids, right? And then we extract water during the chemical reaction. So one of our byproducts for these type of reactions, for these dehydration synthesis reactions, is water. And now where we had two separate smaller items, now we're left with one larger structure, the dipeptide here. And so you'll see this in the formation of proteins, okay? So one of the ways I always remembered what anabolism was, I always thought of anabolic steroids, okay? Those weightlifters would use anabolic steroids to make their muscles bigger. Well, essentially by making their muscles bigger, right, muscles are primarily going to be made up of protein, actin, myosin, our cross bridges there. And so that's what they're going to be doing. They're going to be forming more proteins for that tissue there. Okay, so let's talk about, this is a blast from the past, let's talk about carbohydrates. And so a lot of this we've already covered in the first part of our anatomy and physiology course from chapter 2, but let's just kind of go back and discuss what carbohydrates are. So carbohydrates, right, we classify them into three different categories: monosaccharides, also known as simple sugars, disaccharides, and then our polysaccharides. So carbohydrates are going to come from a couple different types of dietary sources, right? So starch, for example, right, which we'll see like in potatoes, fiber, a lot of plant-based substances will have fiber, and then, like I mentioned before, sugars. So those are primarily going to be our dietary sources in which we get the carbohydrates, all right, from sugars, starch, and fiber. So let's start off talking about our sugars, right? Our sugars, we're going to begin with the monosaccharides, the simple sugars, glucose, fructose, and galactose, okay? Glucose, fructose, and galactose are our monosaccharides. Now what we're going to do is we're going to form our disaccharides. Disaccharides are always going to have at least one of those sugars being glucose. Okay, so it could be glucose and fructose, it could be glucose and galactose, or it could be glucose and glucose. So that's what we're going to be dealing with here when we're talking about our disaccharides. So our disaccharides, we have our sucrose, which is our table sugar. Then we have lactose, right? Obviously, lactose, milk sugar, and then maltose, which we find in a lot of our products. For example, if you're eating Fruit Loops, okay, you'll see maltose in those types of products there. So we'll go through, and actually I'll get into a little bit more detail here later on about which sugar contains what. So moving on to starch, this is a polysaccharide, so it's going to have many molecules, all right, sugar molecules or glucose molecules, basically forming a chain. So we call that a polysaccharide polymer. So it's just a long string of these molecules here. And so during the digestive process, we just start to make that long string into much smaller strings, and then eventually into the individual. The goal is to get them to the individual monosaccharides here. So consider starch to be just a long string of these glucose molecules here. All right. We also have our refined starches here, which we'll use like cornstarch. Cornstarch is wonderful if you're cooking and you are making like a gravy, or although I'm not a very good cook, so don't ask me for good recipes. But if you're trying to thicken something up, if it's too soupy, okay, cornstarch is wonderful to use, right, when you're trying to thicken something. Fiber, we're all pretty much familiar with fiber. Fiber is the stuff that helps you to stay regular. When I say helps you to stay regular, what I mean is to have regular bowel movements, because fiber, all right, cannot be chemically digested. And if it can't be chemically digested, it's going to remain in the GI tract and be excreted, all right, during the defecation process. So we cannot chemically digest it, and we cannot absorb it. So what do? We just get rid of it. So you can get fiber from both plants and animals, but predominantly a lot of the fiber that we consume will come from plants. So some of the sources: lentils, peas, whole grains. This is a big issue with folks that have diabetes, is that when they're having issues with blood sugar levels, it's usually encouraged that they increase their fiber intake, because it helps with the absorption of sugar at a more regulated pace for the digestive system, so they don't crash or have any sugar issues. So let's start off with our famous molecule, the glucose molecule. The glucose molecule, all right, 6-carbon molecule. It is a monosaccharide, and here is a very important fact. It is the primary nutrient for getting energy to our cells. Cells love glucose. Your brain loves glucose. In fact, your brain gets top billing when it comes to your glucose supply in your body. And so therefore, we have to maintain the appropriate amounts of glucose. And so again, we learned way back when we studied the endocrine system how important it was to have that balance with those hormones, especially glucagon, cortisol, insulin. Insulin's the big one, all right, that helps to maintain, all right, your blood glucose concentration levels. So what happens when the body wants to hold on to glucose? Well, it's not going to just excrete it, and it will in some situations. We've already talked about those situations. You know, diabetics, right? They are going to spill glucose to the urine. But in healthy individuals, let's say we have someone that has no issues whatsoever, okay? They just had a nice meal, and your body is a hoarder. It wants to hold on to things. It's like that relative in your family that never cleans out their garage or closet, and you ask them, hey, you know, Uncle Pat, you got to get rid of this stuff. And Uncle Pat's like, oh no, heck no. Oh, I might need that. I might need that for a later time. Well, that's what your body's like. So it wants to hold on to glucose for another time. So it's going to store it. And so it's going to store it in the form of glycogen. And so it does it in 2 of our organs, in the liver and in our skeletal muscle. And so glucose gets stored as glycogen, all right, when you have extra glucose. And so it's going to store it as the glycogen molecule, right? And that process of storing it is called glycogenesis. The first part of glycogenesis represents glycogen, and then genesis means to make, create, okay? So that process, that glycogenesis, is this making of the glycogen molecule, and all that is just a long string of individual glucose molecules attached to one another. So there's going to come a time when you need to access that stored glucose, that glycogen. And so that process is called glycogenolysis. So here, when we're looking at this word, glycogen, right, is telling us what we're dealing with here. And then lysis is to break down. So all we're saying is this process of glycogenolysis is we start to break down, all right, the glycogen molecule, and we start cleaving off individual glucose molecules. And the process, that chemical reaction that does that is hydrolysis. So the liver will hydrolyze, right, glycogen, basically just cutting off pieces. I think I have the slide right here. Here you go. Here's our glycogen molecule on the right side of our screen. So the liver is just going to start hydrolyzing this, just cutting it off. Cut and cleave and cut and cleave. And it will just knock off those individual glucose molecules and dump that into the blood. So that is the process. It's called glycogenesis. And so now we have these individual glucose molecules that we just got out from the liver or the muscle. And so they're floating either in the blood, or if we're dealing with the muscle, they'll stay in the muscle and be broken down for ATP. Well, that process is called glycolysis. So when we break glucose down into ATP, that process is called glycolysis. Now, there might come a time when we need to make glucose because we don't have enough on hand. Well, your body's really creative like this. And so it's like, I've got a solution. I'm going to make glucose from what we call non-carbohydrate sources. So what's a non-carbohydrate sources? Proteins and fats, right? Amino acids, fatty acid chains. Those are non-carbohydrate sources. So we're going to utilize those non-carbohydrate sources to make glucose. Well, the superstar in that scenario is the liver. The liver is the organ that is going to use these non-carbohydrate sources to make glucose. And that process is called gluconeogenesis. So gluco for glucose, neo meaning new. So we're going to make some new glucose, and genesis is to make, build, create. So a lot of times when you look at these words here, I really want you to think, okay, I have no idea what this means at first glance. Try to dissect the words. Try to dissect those words to see, to come up with a helpful hint as to what it does. All right, some of our other carbohydrates, right? We have our hexose monosaccharides, which are isomers. And isomers are going to be, all right, these structures that are similar to another structure, in this case, glucose, right? Galactose and fructose are going to have, all right, the same molecular formula, okay, but they are going to vary in their structural formula. They're going to appear different, but they're going to have the same number of hydrogens, the same number of oxygens, and the same number of carbons there. Then we also have another type of monosaccharide, and that's going to be our ribose and deoxyribose, which are our pentose sugars. And we call those pentose sugars, pentose means 5 carbon, or 5. And so these are our 5 carbon sugars here. All right, so on to the other types of sugars that we have, the disaccharides. I was talking about this earlier on. Our disaccharides are when we take 2 individual monosaccharides and we attach them together. Right, and so that gives us our sucrose, lactose, and maltose. Keep in mind, like I said, every single one of those disaccharides have at least one glucose molecule in that structure there. And then it'll be bonded to either galactose, it'll either be bonded to fructose, or it will be bonded to another glucose molecule. All right, and then finally our polysaccharides. Right, well, we just got done talking about one, the glycogen. All right, the polysaccharides are going to contain, obviously, poly meaning many, so 3 or more sugars. So our glycogen is the most common one that we find in animals. Now, when we're dealing with plants, that's where starch and cellulose come from. Okay, so plant starch is wonderful Okay, wonderful when you want to get a lot of glucose in its stored form, right? And then you can break that down and start to get glucose out of that starch. But then we have our cellulose. All right, now that is going to be a non-digestible fiber. And the big reason for that is because our body has a very difficult time in breaking down, okay, the cell wall. Now, if you've never taken a biology course that when you're learning about animal cells versus plant cells, one of the big differences between an animal cell and a plant cell is that plant cells have a cell wall. And that cell wall, all right, helps to give plants their rigidity. Without that cell wall, they just be all floppy. Right? So it plays a big role in that. But that cell wall, all right, that cellulose there is also going to be non-digestible. So if it's non-digestible, it can't be absorbed. And if it can't be chemically broken down, it's just going to be passing through. It's like that hitchhiker. It's just passing through, or that hobo that comes through town. It's going to pass through our body, and then we'll get rid of it. Okay, so here you can see on this slide here, just some of our simple carbohydrates, right? We've got our monosaccharides at the top there, the 6 carbons, the hexose sugars there, galactose and fructose. Then to the right of that, you can see the 5 carbon sugars, our pentose sugars, ribose and deoxyribose. Those should look familiar too, because if you've heard of DNA and RNA, you got it. That's where those sugars are going to be found. Then you can see here in our disaccharides, notice, right, you have at least one glucose molecule in all of our disaccharides. Always at least one glucose molecule there. Okay, so keep in mind, just to review, sugars and starch, these will be converted into glucose. All right, our glucose is our primary energy, all right, in our cells here. Okay, but keep in mind, this is an interesting fact, it is not considered to be essential. And the reason why is because we can make it through gluconeogenesis. So folks that go on a completely sugar-free diet, no carbohydrates whatsoever, all right, they're not taking in carbohydrates, but guess what? Their body's going to be making carbohydrates. If all they're eating is fats and proteins, okay, their body is going to convert, all right, those non-carbohydrate sources into glucose. All right, big deal there. All right, one more thing about fiber. Yes, I said it helps to keep you regular. Okay, so it does stimulate peristalsis, which is that movement, all right, through the GI tract there. But another big factor for fiber in the diet is it helps to lower cholesterol. And also, like I said before, it also helps, all right, to keep your blood sugar levels more balanced, meaning you're not going to have these large swings there. Talk to any primary care doctor, all right? For folks that have diabetes, they're always big on making sure that they're taking in a decent amount of fiber, right, to help regulate their blood glucose levels. Okay, so our next macromolecule is going to be lipids, also known as fats. Okay, so a couple characteristics of lipids. One, they are water insoluble. What does that mean? Well, let's put it into a practical image here. If you are cooking on your stove and you want to make some pasta, okay, put the water in, get it to a boil, all right, or not necessarily get it to a boil, but you put the water in, and then some folks will add a little bit of oil, olive oil, whatever kind of oil. But you'll notice when you look at it, you'll see that the oil doesn't separate or dissolve. It stays kind of congealed at floating on top of the water. That's because it's water insoluble. It will not dissolve into the water. That's what we're talking about. So lipids are water insoluble. They will not dissolve in water. All right, so the primary purpose for lipids is going to be for energy. It's a stored form of energy. Also, it makes up a huge amount of the cellular plasma membrane there. Remember phospholipids? Big time. And then we learned back in the endocrine chapter, chapter 17, right, that our lipids are used to make hormones. So there's 4 classes. We have our triglycerides, our phospholipids, our steroids, and our eicosanoids. So let's review triglycerides. When you hear the term triglycerides, you should be thinking energy storage immediately. Energy storage. Okay. So remember what I said, your body is a saver. It's a hoarder. It never wants to get rid of anything that it could use for later possibly. And so what we're going to see here is, and when you go over chapter 26, if you haven't already, which is the digestive chapter, right, we'll kind of talk about how we break down, okay, fats and proteins and whatnot, and what some of the products are from that, right? But triglycerides are made up of our glycerol backbone and 3 fatty acids. Now, the fatty acids don't all have to be the same. They can vary. So when we classify the length of our fatty acids, we have our short chain fatty acids, our medium chain fatty acids, and our long chain fatty acids. We're hearing a lot about the medium chain fatty acids a lot because there's a big push with some of the dietary benefits from our medium chain fatty acids. Okay, but keep in mind, all right, the length of the fatty acids will vary, but also the number of double bonds will vary. So if we're dealing with a saturated fatty acid, that means there's absolutely no double bonds. If we're dealing with an unsaturated fatty acid, then we have at least one double bond. If there's more than one, 2 or more, then we call it polyunsaturated. So let's talk a little bit about our adipose tissue, okay? Adipose tissue is a connective tissue. It's one of our loose connective tissues, right? And this is the tissue that's going to store our triglycerides. So if we're going to talk about adipose tissue, we have to talk about lipogenesis or lipogenesis and lipolysis or lipolysis, right? So when you, again, dissect the word lipo, all right, then genesis, all right, that is to create fat. So when we're talking about lipo or lipogenesis, we're talking about making triglycerides. And we do this, all right, when we have lots of stuff or excess nutrients are available to make the triglycerides, because then we're going to store them for later. All right, then the other process is lipolysis or lipolysis. And this is when we break down the triglycerides. And this is usually when we need some energy. Okay, we need what's stored in those triglycerides, right, which will be the glycerol and the fatty acids or whatever it composes those structures. And we need those for whatever, maybe for some metabolic purposes here. So here you can see on our picture at the top, here's our triglyceride. So we'll write it out into the molecular formula here. Here's our glycerol backbone. And then we have our 3 fatty acids attached to it. And you notice that these 3 fatty acids are different from one another. All right, so we have an unsaturated, we've got some saturated, okay? So they all vary from one another, and they also vary in length. Okay, so they're not all going to be the same. So this right here, all right, when we have our triglyceride here, that is going to be made as a result of lipogenesis. Okay, so now when we want to break down our triglyceride, that process is called lipolysis, and we're going to, during that process, okay, we are going to cleave off the fatty acids from our glycerol backbone there. All right, phospholipids are the next type of lipids. Right, and so these phospholipids, right, like I said, they are a major component to our plasma membranes there. And they literally will form a barrier, okay, between the internal environment of the cell and the external environment of the cell. So phospholipids are very similar to triglycerides, except they only have 2, okay? Let me just show you. Here is our triglyceride. So you have the 3 fatty acids hanging off. Well, a phospholipid has 2. Okay, so our phospholipid has the glycerol component to it, And it has, and this is important to know this, it has the polar phosphate group. And then our fatty acids, that is going to contain the non-polar component. See, phospholipids are what we call amphipathic molecules. That means that molecule, part of that molecule is polar, and then the other part of that molecule is non-polar. So the part that is polar is going to be the glycerol, phosphate molecule, and any organic groups that are attached to it. And so we refer to that as the head. So since it's polar, it is hydrophilic, meaning water loving. So that part of the molecule loves to be exposed to water. It can be in water all day long. So where is there a lot of water? Well, there's a lot of water outside of the cell. And believe it or not, there's a lot of water inside the cell. But if you recall, our cells have that phospholipid membrane there, but to be more specific, we call it the phospholipid bilayer. And that bilayer means we have two layers of our phospholipids, but here's the thing, the heads are going to be away from each other and the tails, right, are going to be facing one another. Now, I'm not going to take the time to draw more of these, right, but that's the phospholipid bilayer. And so the heads are going to be exposed to the internal and external environments of the cell there. Now, the fatty acid part, the tails there, those are nonpolar. And so those are hydrophobic, water-fearing. So they're not really going to be exposed to the water, so we keep them on the inside of our bilayer there, so you never have to worry about it. All right, on to our third lipid, that is the steroid here. We've heard of steroids, and we've learned throughout the course some of the purposes of steroids. We'll talk about it here in a moment, all right? But steroids are, one, hydrocarbons. So that means that they are made up of hydrogens and carbons. That's what we mean when we're dealing with hydrocarbons. And they are multi-ring structures. I do think I don't have a picture of it here in my slideshow. All right, but if you really want to know, go into the textbook and check it out. All right, what we will see, all right, we have 4 carbon rings. I won't even try to draw it and insult you, but here's what's important about our steroids, because our steroids will have differing side chains. So a side chain is just this little extension coming off of one of our rings, one of the molecules there, and it can vary. And so depending on, all right, what that side chain is, all right, it will differ what those steroids are. So cholesterol, for example, all right, one of the primary steroids in our body here, right? In fact, we need cholesterol. It is our precursor when we want to make steroids. So that's why I tell people all the time that cholesterol, right? Yes, it should be carefully monitored, right? But you need to have cholesterol in your diet, all right? Because, all right, one, to make steroids, but also, right, we need cholesterol in our cell membranes. If you recall, when we talked about the cell in chapter 4, okay, the cholesterol, when it's added into the plasma membrane there, it allows the plasma membrane to be more tolerant to handle temperature extremes. Okay, so cholesterol is very important in that regard. Right, another, all right, difference, all right, when we're dealing with our steroids, all right, we have our steroid hormones, both male and female, testosterone and estrogen. And then finally, we have our bile salts, again, talked about in digestive chapter here, but our bile salts help to break down, it's called emulsification, helps to break down our lipids. Remember, we're starting with something big and we want to make it into something smaller. Our final lipid to talk about is the eicosanoids. And we talked about eicosanoids back in chapter 17, when we were talking about the endocrine system, about locally acting hormones. And that's basically what they are. They are locally acting hormones or local signaling molecules here, right? They come from arachidonic acid. Now, arachidonic acid is found in your plasma membranes. So if you damage that plasma membrane, then arachidonic acid starts to undergo a chemical reaction cascade. And we call it the inflammatory cascade. And it's a series of chemical reactions. And so these chemical reactions, all right, are going to yield us, all right, these different classes of eicosanoids, and they're listed below here. You can see prostaglandins, prostacyclines, thromboxanes, and leukotrienes. Right? They have several different, all right, properties, but they play a large role in the inflammatory response that we see during times of injury or physical assault on our cells. Okay, and so they have different properties. I'm not really going to talk about that here, right? But they also will play a role, right, when we're dealing with the way our nervous system is able to communicate, right, with our tissues here. So keep in mind, eicosanoids primarily in inflammation. All right, so one of our clinical views here, talking about saturated, unsaturated, and trans fats. Ooh, the evil trans fats. Watch out for those. All right, those are actually illegal in New York City. All right, you cannot serve or use products that have trans fats in them, all right, to paying customers here. Okay, now you can buy it for yourself at home, do whatever you want, but you cannot sell that to paying customers in New York City. That has been outlawed. So most of our animal fats are going to be saturated. Now, one thing you have to understand when we're dealing with fats and oils, for example, fats and oils are really considered to be the same thing. Okay, an oil is just liquefied fat at room temperature. Okay, and then usually when people are talking about fats, like for example, butter, all right, that is going to be a solid at room temperature. So they're very, very similar in that regard. I did a seminar and one of the instructors said that one time. He said, all right, the difference between, all right, fats and oils is one is liquid at room temperature and the other one is solid at room temperature. So most of our animal fats that are saturated, they will be solid at room temperature. Now, when we're dealing with vegetable fats, all right, those will be liquid at room temperature. Those are going to be unsaturated. Okay, and unsaturated fats are considered to be healthier. And so we can make them, all right, into saturated fats, and that process is called hydrogenation. And then from hydrogenation, we developed the trans fats because what we did basically was, all right, when we go through that process of hydrogenation, we just didn't complete hydrogenation. So we stopped, I won't say midway, but we didn't complete it. So we call that process partial hydrogenation. And partial hydrogenation led us to the trans fats. So we never completed that process of converting them, all right, from unsaturated to saturated. And so we wind up with the trans fats. Unfortunately, they taste delicious, but they're not healthy for you. They do increase your likelihood of cardiovascular issues like heart attack and stroke. So we do recommend people to stay away from trans fats. All right, so trans fats, get as far away from them as you can. All right, so our polyunsaturated fatty acids, I talked about those before. All right, we're going to see that those are going to have 2 or more double bonds, right? And these will be at room temperature liquid. So we enjoy these. These play a healthier role compared to our solid, all right, fats. But you'll see oils, sunflower oil, soybean, safflower, corn oil, all of those, all right, are going to be polyunsaturated fatty acids. All right, then we have our cholesterol. Like I said before, cholesterol is very important when we're dealing with our plasma membrane, makes it healthier to handle temperature extremes there, right? But cholesterol is needed, all right, to make our steroid hormones, right? It's our precursors, what we begin with. We also need it for our bile salts. And I didn't mention this before, but vitamin D. Vitamin D, okay, really now should be considered a prohormone, right? We don't really consider it too much to be a vitamin so much. We found so many more purposes for it, right? But vitamin D, we need it for the resorption, or the absorption, I should say, of calcium from the digestive tract. Plays a huge role in our immune system. I could go on and on about it, but I'm not going to, all right? But we can get our cholesterol through our dietary intake, or our liver can make cholesterol too. So let's talk about that. How do we make, all right, cholesterol? Well, we'll go to the liver. The cells of the liver that are responsible for this are the hepatocytes. And so I'm going to kind of start you through the story, walk you through the steps, all right, of how we make, all right, cholesterol in the liver. All right, so let's, and I'm going to be going through back and forth through these pictures here, all right? So back and forth, back and forth. All right, so let's start off here with our fatty acids. And so our fatty acids are traveling through our blood. Let's just say you just had a nice meal, you digested it, you broke it down, all right? We had that catabolism undergoing the digestive process there. We broke down all those different carbohydrates, all those different types of fats, all those different types of proteins. And now we have our fatty acids floating around in our blood. And so what will happen is we are going to break down those fatty acids into a molecule in which we call acetyl-CoA. Right? And it is a 2-carbon molecule. And so we need acetyl-CoA, right? Because that is going to be our starting point to make our cholesterol, because we're going to build onto that 2-carbon unit there. So that beta oxidation is the process that we break down those fatty acids, right, into that acetyl-CoA. So we saw that big, long fatty acid, and all we started to do is just cleave off those carbon, all right, units, all right, a little at a time, more and more and more, until we're left with the 2 last carbon units. That's the acetyl-CoA. So now we're going to build up our cholesterol molecule. And so in order to do that, we need this very important enzyme. It's called HMG-CoA reductase. This is going to get that process going here. And so from that, all right, that beginning point with the acetyl-CoA and with that enzyme, we are going to wind up with our cholesterol here. So if I zoom in here, kind of show you, here's our fatty acid floating through the blood, okay, enters into the liver, into the liver sinusoid there, exits out of the sinusoid, enters into the hepatocyte, and then the hepatocyte undergoes that beta oxidation, just starts cleaving off these carbons here until you're left with this 2-carbon structure here that are acetyl-CoA. And then you're going to undergo a series of enzymatic reactions, but we need our HMG-CoA reductase to start all that off. And then we wind up with our cholesterol molecule. Now, here's the thing. This pathway is going to be influenced by a couple of different things. One, how much cholesterol that you are naturally taking in through your diet. If you're on a high cholesterol diet, then the hepatocytes aren't going to be making a lot of cholesterol. If you're on a very low cholesterol diet, then we're going to increase the amount of cholesterol that the liver makes. So you can see here in our picture, okay, we're going to use cholesterol here to make our bile salts. So when you have a nice fatty meal, all right, those bile salts are going to be excreted into the small intestine and travel through the small intestine and large intestine. While they're doing that, they're going to be emulsifying or breaking down, right, your fats there and into our smaller subunits there. And then those bile salts will be resorbed, right, through the digestive tract, right, and very little of it gets lost in your feces. Roughly about 10%. The majority of it is going to be resorbed and then reused, right, for another time. Okay, so now we've made our cholesterol, and now what are we going to do with it? Well, a couple different things. We can use it, all right, to be made into bile salts, or we can use it to make what we call a VLDL, which stands for very low density lipoprotein. And a lipoprotein is just going to be a protein with lipids that are surrounding it. And so now this is probably where you probably learned about good cholesterol versus bad cholesterol. And we'll discuss that here in a moment, all right, what the lipoproteins are. Okay, so like I said, our lipoproteins are just these proteins with a lipid, all right, wrapped around it. All right, we talked about this a long time ago, well, way back when in chapter 2, but in chapter 26, about the digestion, about chylomicrons, all right, that those chylomicrons are lipoproteins here. So our lipoproteins, there's 3 different types that I want to talk to you about, okay? And they are measured or named by how dense they are. All right, so we have our VLDLs, which is the very low density lipoproteins. So this one here is pretty much going to be mostly lipids. Then we have our low density, okay, which is going to be less lipid. And then obviously our high density lipoproteins, these are what we call the good cholesterol. They have the least amount of fat. The least amount of fat. All right, so here's what's going to happen. The liver creates these VLDLs, these LDLs, and so these VLDLs and LDLs are going to leave the liver and go out to the peripheral tissues. When I say peripheral tissues, all over the place. Okay, it could go out to the skin, it can go out to muscle cells, it can go out to epithelial cells, cells that need, all right, these lipids, all right, this fat, for whatever purposes they need it for. So let's start off with the VLDLs. So think of the VLDLs. They're going to just head out into the blood, okay? And they're going to circulate throughout. And basically what they do is they're going to release the fat, the lipids, triglycerides specifically, to those peripheral tissues. Now, of course, where do we store triglycerides? Primarily in adipose tissue when it's time for storage. Or we can use triglycerides for energy production. Right, so, but primarily, the VLDLs are going to search around and head out to the adipose tissue. So when they offload some of those triglycerides, the VLDL is no longer in existence and now converts into a LDL because, like I said, it offloaded some of the lipids there. Those triglycerides have now been offloaded into the adipose tissue. So it's like driving your car and the gas tank is getting less and less the more you drive, right? That's what we're seeing here. So our low density lipids, all right, will have less fat, all right, but we'll see that they have high amounts of cholesterol here. So our LDLs will travel around to the cells, and so they're going to drop off the cholesterol. How do they do this? Well, specific cells will have receptors. We've talked about this before. And so the LDLs will bind onto those receptors, onto the cell. And once that occurs, then the cell is going to encapsulate it through endocytosis. And it's going to create a vesicle. And it's going to pull it, all right, into the cell. So we'll see, all right, whatever that cholesterol is going to be used for. We talked about some of the purposes. It could be a gland in which it needs to make more hormones. So we'll see it being used to help make some of those steroid hormones, right? Testicles, right? Also in the ovaries there. All right, so once this happens, all right, I like this picture right here that shows the pathway here. Kind of go through this. So here is our hepatocyte. It's now made the cholesterol, all right? It's got the triglycerides. So it packages it all up into the VLDL. And so it shoots it out into the blood here. So like I said, the VLDL travels out to the peripheral tissues there. It's going to come in contact here with the adipose tissue. And so what it'll do is it will drop off some of the triglycerides there. So it drops off the triglyceride. You can see the yellow is now decreased. It looks like it's a little bit lower. right? So it's offloaded some of the lipids. The triglycerides are now hanging out in the adipose tissue needed for a rainy day. So now our LDL wanders throughout the periphery again, and then it's going to head, all right, to another peripheral tissue cell, one that might need some cholesterol. So it has the receptors out and waiting, like a catcher's mitt, waiting to catch the ball. Right? And so the LDL will bind with that receptor, and then that cell will then pull it into the inside of the cell for whatever purpose. Okay, it might need that cholesterol for the plasma membrane. It might need that cholesterol to make some hormones. Okay, so whatever that cell needs it for, it has it. After that point, okay, we'll see. Now let's go back to the liver and talk about the last type of lipoprotein, and that is the HDL. I always think of the HDLs as the molecules that wander around and just kind of suck up cholesterol and suck up triglycerides. That's basically what they do. So let's talk about these guys, and then we'll end the slideshow here. All right. So look, these proteins, these HDLs, right, are made by the liver, and so then again they are shot out into the blood. Except their situation is they have the least amount, all right, very little lipids there. So they're basically empty. And so they're going to go and wander around throughout the bloodstream, and they're going to go and try to fill up on lipids from any of our peripheral tissues here. And that's what they do. So like I said, they're going to absorb that up. They're similar, all right, to the LDLs because they can also provide cholesterol, all right, to the cells that will make steroids. All right. But here's the thing. The difference is HDLs are not going to undergo endocytosis. Right? HDLs do not have to do that. So eventually they drop off all their stuff, right? And so, or not drop it all off, excuse me. They pick up all the LDLs. So where do they go? They go back to the liver. And so they drop off all of the lipids there, cholesterol, all right, triglycerides, whatever they picked up. And then they allow the liver then to use that cholesterol to maybe make more bile salts. So it's really a kind of a cool process. So let's take a quick look here. All right, so here you can see liver just made, all right, it's HDL molecule, pushes it off into the bloodstream, it circulates around, it starts filling up on stuff. Maybe it picked up some triglycerides and some cholesterol that were in some tissues there or just floating around the blood for all we know. And so it goes around, fills up, and then goes back to, think of the liver like a dumping station, right? It picks up all those cholesterols, all molecules and triglyceride from the peripheral tissues there and anything that's inside the blood vessel, and it returns it back to the hepatocyte full. And so now it can offload all that cholesterol and those triglycerides for, like I said, bile salts or to make more VLDLs. Okay, let me just hit this last slide and then we'll be done. Okay, so of course, when we're talking about good cholesterol versus bad cholesterol, high levels of LDLs, right, or your total cholesterol is not considered to be good. Right? This increases your chances of cardiovascular disease, right, which then increases your chances of heart attack, stroke, right? So high levels of LDLs, high levels of cholesterol, bad. Low levels of HDLs, because remember, that's the good cholesterol. That's the cholesterol that wanders around and sucks everything up and returns it back to the liver, okay? So that too is bad. So low levels of HDLs, bad. High levels of LDLs or total cholesterol is also bad. So anything over 200 milligrams per deciliter, when you go in and get your blood drawn, and they go and you look at your cholesterol, so one of the first things that my patients do is they'll tell me if their cholesterol is good or bad, and they usually give me a number around the 200 mark. If it's, I've heard numbers 260, 220, all right, you're above, so you're considered to have high cholesterol. That's when some patients might want to consider some lifestyle modifications or possibly taking some medication to help with that. So keep in mind, okay, LDLs, bad, HDLs, good. Right? And so we want to see high levels of HDLs in circulation because they'll take any lipids that they come in contact with, whether it's on the inside of the blood vessel wall, all right, or from our peripheral tissues there, and they'll take it back to the liver there to be used for whatever that the liver needs it to be used for. All right, folks, we're going to stop here and call it quits. I hope everybody does well, has a great day, and I will talk to you soon.